Okay, so this is number 15 in the homework. We've got a planet, and we know its mass. It has a moon that's going around, and its speed is known. They tell us the speed of this planet, whatever it is, or the speed of this moon that's going around the planet in an orbit. It's going around in a standard orbit. And they want to know what is the distance between their centers of mass, this distance r here. So there are two ways to calculate the force that's holding the moon and the planet together in this orbit. What are the forces? What force is holding these things together?
Gravity.
The gravitational force. So how do we calculate gravitational force between two objects? It's the big G times little mass times big mass, right? All over, what is it over? Nope. Radius squared, or the distance between them squared, right? Oh, this picture is backwards again. How do I fix that? I can't remember how to fix it. Oh, I remember how I did it last time. Let's see, I used my zoom, right? There we go. That's better. Okay, so now it should be seeing, yes, now it's straight. So this is one way to calculate that force between these two objects. But this is also a kind of, the force that's holding this thing in orbit is also a centripetal force. So we can also say that this force is equal to the centripetal force, which would be the mass of the object that's going around, which is the mass of the moon, the little mass, times v squared over r. So in other words, we get these two things equal to each other. We get big G times little mass times big mass over r squared equals little mass times v squared over r. We know v, we know big M, G is a constant, and little m is going to cancel out. Can we calculate r? We can solve that for r, can't we? So this is a little bit tricky where you're going to take two concepts, the concept of centripetal acceleration and the concept, or the centripetal force, and the concept of gravitational force, and combine the two because they're amounting to the same thing, right? They're both calculating the same force using different numbers. But since we don't have the mass of the moon, we can use them both, cancel out the mass of the moon, and then calculate the radius. Once you have the radius, you can calculate the mass of the moon even. Any other questions?
It ends up being mass times velocity squared radius.
So when we actually solve this right here, we're solving for r. We're going to cancel out one of the r's as well that's in the denominator. And so the equation looks like this when we solve it. G times big mass, mass of the planet, divided by r equals v squared, right? Because everything else has been canceled out, and we want to know what r is. So what we do is we multiply both sides by r and divide both sides by v squared. And we get r equals gravitational constant times mass divided by v squared. The gravitational constant is whatever it is, something times 10 to the minus 11 or something, right? Some tiny number. Then the mass of the planet divided by the velocity squared, and you're going to get the radius between these two. So what was the mass of the planet? Some other huge number, I'm sure.
The mass of Earth is...
It's not doing Earth. It's just a planet. 3.29 times 10 to the 26 in this problem, in my problem. So that one you would multiply by g, which is 10 to the minus 11, so you get 10 to the 20, or you get 10 to the 15, and then you would uh, divide by the velocity squared, which was 10 to the 3, so you get 10 to the 6. So you get about 10 to the 9 for the radius, about a billion meters. Give or take. All right. Then somebody said they wanted to look at 16. Yeah? 16 is a beast. So we've seen this one before, but we couldn't finish it because I put it in the wrong assignment. And I tried to remove it from that assignment last year, but it didn't. I think I have to rebuild the assignment from scratch, which really kind of takes me off. But I guess I'll do it eventually. But here we have the race car problem, except on the banked turn, banked curve, right? And we're going to let's see. We're going to assume, I think, that this turn is an ideal banked turn so that it doesn't slide. The car will not slide even if it's frictionless here. So we're going to assume that it's banked perfectly. And what that means is that our force is going to be, our force, there we go. I thought I could put a picture in here, but I guess I can't. Oh well. I'll just draw it in, I suppose. So we've got this car that's on this banked curve like this. Right? We put our car up here. Man, that's a terrible car. I'm just going to draw the car as a box. Okay, so there's our car. I'll get rid of this thing. So the forces that are holding this thing up on here, well, what are the forces we have? Let's just talk about the forces we have. The forces we have include gravity, the weight force, which equals the mass of the car times gravity. Right? We have the normal force of the surface pushing up on the car. Right? And that's it. Those are the only two forces really acting on the car. So which of these forces is responsible for holding the car in its turn? Right? Well, it's going to have to be a force that is centripetal, which means it's going to have to be pointing this way. So we're looking for forces that are pointing this direction, right? Because the turn is around an axis out here, and so we're looking for forces that are pushing in this direction. Well, the weight force is pointing perpendicular to that direction. So it's not pointing in that direction. However, if we rotate our axes to this, then we can actually start to see something that's going on here. The normal force is partially pointing in the direction of this guy, right? And which part of it is doing that? In fact, we don't even have to use a rotation of axes. Let's erase that rotation of axes. I don't think we'll even need it. Not at the moment, anyway. But we're looking for a force that's pointing in this way. And if you remember when we did this before, we talked about the fact that our weight, part of our weight, is counteracting the normal force, right? And part of it is being taken care of in some other way. So this part right here, this is the part that's trying to make the car go down the track, right? So what we can say then is that part of our normal force, so instead of looking at the weight force this way, let's look at the normal force in this kind of way. We can say that part of our normal force is pointing this way, and part of it is pointing this way, right? So we have a component of our normal force pointing inward and a component of our normal force pointing upward. That inward pointing normal force is the centripetal force. It's the only force that's pointing in the direction of the centripetal force. So that is our force centripetal, and it happens to be equal to, if we know one of these angles, which we do, and it's not obvious which angle we're going to know here because I didn't draw these triangles as extreme as I wanted to. So if I draw my triangles a little more extreme, a lot more extreme even, then it will start to become obvious which angle this is. If our normal force is up this way, oops, up that way kind of, right? And the one that we're looking at is this one, then this is obvious the same angle as this one, right? In this triangle. So this is obviously the opposite side from the angle theta. This is the angle theta, this is the angle theta. So our centripetal force is going to equal our normal force times the opposite side, which is going to be a sine of theta, right? Since it's the opposite side. Now we just have to figure out what our normal force is. Well, we knew how to do that. We've done that before. We do that by tilting our axis. Now we go back to the idea of tilting our axis and then calculating this component of the weight force, use that component as our normal force, then use that normal force to calculate this component of the normal force, which will be our centripetal force. So it's like a component of a component kind of thing here. Now let's go back and see what the actual problem is going to have us do, because it's going to have us do several things here. So they want you to calculate the weight of the car first. Hopefully that's not hard for you to do. If it turns out the car wasn't moving, the normal force on the car would be equal to the component of force of gravity. There would be some necessary friction between the tires and the track to keep from sliding down the bank. But our problem, it's moving around the turn and getting turned by the 3D shape of the track, which actually makes the normal force larger than the weight of the car. Let's say the driver wanted to go around a turn at the perfect speed where the car wouldn't want to slide up and down. Wouldn't go. So what's the normal force on the car in this situation? So what is the normal force on the car? Well, in that case, what we have to do, since the car is now moving, right, then we have to assume that there is a centripetal force that is equal to what we understand about the centripetal force of a car moving at a particular radius of track. What do they say about the radius of the track here? Or do they say anything about that? Force equal to track use track.
Let's go through this several times. I remember putting this down here. Net force is equal to the centripetal force, or in magnitude.
In this one?
I don't know if that was correct.
Oh, the normal force, you mean?
No, I put down net.
So yeah, this is normal force. The net force is the next one. And the net force is the centripetal force. That is correct. But I'm trying to figure out how we're going to calculate this with what we know about the, is this a number? So the normal force on the car, turns out if the car wasn't moving, in our problem it's currently moving around the turn, makes the normal force larger, which is true. So what happens, I guess let's explain this first and then let's try to figure out what numbers we're supposed to use here. Go back to zoom. What happens when it's turning is that when it's turning around the track, your net force is the centripetal force pointing inward, and they say, well, it's bigger than the normal force when you're stopped, and that's true. But the reason for that may not be obvious. The reason that the normal force gets bigger, the normal force gets bigger, is because it has to point in a direction that's going to affect the normal force. We've already determined from this picture that the normal force is in the same direction as the centripetal force. So if it's just sitting still, the normal force if it was just sitting still, the normal force is the thing kind of holding it in place then. And so you'd have to have friction. If you don't have friction, then you have to be moving in order for it to sit there, to stay there, right? And if it's moving, then there's a centripetal force that is pointing in the same direction as this component of the normal force. So it's going to add to that normal force. So the overall normal force is going to increase, and that's going to come from the centripetal force. Now, the thing that's confusing me at the moment is, have they given us the information that we need to know for the centripetal force? They give us the mass of the car and the angle of the track. Oh yes, they do give us enough information. Why do they give us enough information? Because we've done this problem before. So we should remember that we've done this problem before so that we can not have to reinvent the wheel. When did we do this problem? Of course, we did it in the book. So let's go to the book. I'm sorry? No, we did it in chicks. We did it just on Tuesday. So on Tuesday we talked about this fact that if you bank the curve at just the right angle for just the right speed, you won't need any friction, and the bank will actually turn the car. So let's go take a look at that. Chapter 6, centripetal force. It was the last example in this section, I believe. Well, only example. Here it is. What is the ideal speed to take on a steeply banked tight curve? We calculated this from doing this problem, which is the same exact problem, right? And this is the angle that we calculated. The tangent of theta is equal to v squared over rg, or v equals rg tangent theta. We have r, we don't have r, we do have theta. Let's see, what do we... We want to calculate one from the other, see what we've got in this problem here. Turn, mass, so if we have this equation here, which will tell us what the angle is if we know the speed and the radius. We don't know the speed or the radius, right? We know the mass and we know the angle. I'm going to have to look at the code of this thing really quick, because I think that they're going to require something of us that we don't have.
Part E or E gives us the radius. Gives us that early.
Yeah, let me see what they're expecting of us at the beginning of this really quick.
While you're in there, can you change the due date to Monday?
Yeah, probably not Monday, but maybe, well, maybe Monday. We could maybe do Monday. This is weight unit, normal unit. I can see.
It's almost like it asks you to replace friction, like figure out what it'd be like if it was sitting still and how much the friction would be, and then turn that friction into something else.
So that's the first one. Here we go, mass, 60. In this situation, okay, I think that what they're saying, I think the question is not very clear here. I think what they're asking for um, they're saying the normal force is essentially equal to the weight times the cosine of the angle. So let's take a look at our picture really quick. So the normal force, which would be this one here, they're saying it's equal to the weight. They're saying it's equal to this component right here. And that's true when it's at rest. So I guess the question that they're actually asking is, what is the normal force of the car at rest in that question? And in that case, we don't need to know the speed of the car. So that's a poorly worded question that I'll have to change. Maybe it will let me edit the question, but we'll see here. So if this one is just at rest, then they want to know what the net force is on the car here. Component of normal force that's pushing it towards the center. And then they want to know the net force acceleration from the net force, and the perfect speed for the radius of the car, turn without friction, that part we did. This is the part that we did in the homework. Yeah, they're asking the question badly, because that's not the answer to it. If I change the question right here, which would be done right here. What is the normal force on the car when it is not moving? Maybe it will let me save this even though you guys have started. Now let's go back here and see if it's been saved here. Chapter 6. Okay, so it changed it. That's good. So the normal force on the car when it's not moving is what we show here. The normal force is canceled out by this force here, the portion of the weight force, which is m times g times the cosine of theta, since we've done that kind of problem before many times. And that's the answer you'll get in that part. But in the next part, we need to answer the question, what is the net force on the car? And that has to be the component of the normal force that's pushing the car towards the center of the turn, making it travel in a circular path in the horizontal plane. So this one should be slightly different. So let's go and make sure that they've asked that question right, since we've already found out one other mistake in this question.
The normal force on the car when it's not moving should be the same as the weight of the car or the zero.
I'm sorry? What did you say?
The normal force on the car when it's not moving.
Yeah, it should be equal to the component of the weight that is perpendicular to the surface that it's on. So in this case, it's the weight of the car times mass times, it's weight of the car times cosine of the angle theta. But the next part of the question is asking what is the centripetal force then? And at this point, this is where we use this is actually where we can use this one right here, this equation. Now, in this equation, we have tangent theta equals v squared over r, but v squared over r also equals centripetal acceleration, right? So this is actually acceleration, centripetal acceleration over gravity, tangent of theta. And if we multiply, so we're going to use this equation, looks like, let me switch to my thing here again. So we have this equation for this situation, tangent theta equals v squared over r times over rg, but I'm going to put v squared over r times 1 over g is the same thing. This right here, though, is the centripetal acceleration. So I'm going to call that centripetal acceleration. And then, so this is tangent of theta is equal to centripetal acceleration over g, right? Well, I'm going to multiply both sides times g, and I'm going to get g times tangent theta equals centripetal acceleration, right? And if I multiply both sides by the mass, then I get mg tangent theta equals m times 10 times the centripetal acceleration, which equals the centripetal force. So we've just created a new equation for the centripetal force doing this. So it's mg tangent theta is the centripetal force. Now the other way to get that, let's see, what is the other way to get that? The other way to get that is to do the thing that I told you before, where we're doing calculate the normal force, and then use the normal force up here to calculate the component of this normal force, and you will eventually get this same formula. You'll end up with you'll end up with a sine theta and a cosine theta, and you'll end up dividing them to solve for the centripetal force in the end. But you will get the same solution. This is just a quicker way to do it. So Now we have a new equation for the centripetal force in a situation like this where you're on a banked curve with no friction, just the curve is turning you. And then we go back and plug in the numbers that we have to get this answer. And this way we don't need to know the speed, we don't need to know the radius, we just need to know the mass, the angle, and we're good to go. So let's go back to here. Check to make sure the question has that right as well. Looks like the question is doing that correctly right here. mg times tangent theta. So we're good. So in that section, that's what you're doing there.
Yeah, but I thought that was like negative 30,000.
For what?
Whenever I do that, it comes out with a negative 30,000.
Wow, you have an interesting calculator.
683 times 9.8.
So 683 kilograms is your car?
Yeah, times 9.8 times tangent of.
Are you using the right units, the right degrees or radians for your tangent? 683 times, are you going to call me a communist to me? What? What's your angle?
33.2. I was in rating.
It doesn't make me a communist, does it?
What?
Doesn't make me a communist, does it?
No, you're just a Democrat today.
Well, I can live with that.
So the net force and the centripetal acceleration the same thing?
Yes.
One spot in there where you, okay, yeah, tangent theta is d squared over r, g. That turned into tangent theta is acceleration over g.
Then you multiplied by g on both sides. So that you had a centripetal acceleration equals tangent theta over or times g, right?
Oh, yes.
And then if you multiply both sides by the mass, the right-hand side becomes the centripetal force. That's mass times centripetal acceleration, right?
Yeah.
This is what we call algebraic voodoo, right? We just start doing things, and you're like, "Why are you doing that? Why are you doing that?" Well, I'm doing that because I see the end of the road. That you guys are kind of walking down the road in the dark, but I've got night vision because I've been here before.
So you're talking about our force net, wait. Our force net and our acceleration for centrifugal should be the same.
No, your net force is equal to the mass times the centripetal acceleration. So that's why we multiply by the mass on both sides. So let's go back to that really quick. We started off with this problem here. We started off with tangent theta equals v squared over r times 1 over g, right? Then I recognize that v squared over r is the acceleration, the centripetal acceleration. That's an equation we know. So I replaced this with acceleration, centripetal. Then I recognized that I had centripetal acceleration over g on this side, so I just multiplied both sides by g to get it on this side. And then I multiplied both sides by the mass, so that I would have mass times centripetal acceleration on this side, which is the centripetal force. The mass times the centripetal acceleration is the centripetal force. So I could just see, I saw ahead because I've been here before, right? It's like if you were taking me to your hometown to the best, barbecue place in your town, I would have no idea that it was in that corner, gas station that doesn't even have a gas pump out front, but it's a great barbecue place. So you're taking me somewhere and I'm completely lost. You haven't even told me you're taking me to barbecue. I just knew that beforehand, right?
My numbers aren't going out.
Well, so far you should have for your centripetal force 4,380 newtons with your numbers. Does that sound right?
Yeah, that's for the, what is the net force?
That should be your net force.
So then you gotta take that number and times it by the mass to get acceleration.
No, I mean, you're done with that. You don't need,
Alright, now,
does it even ask for acceleration? I don't know.
yes, it does.
Where does it ask for acceleration? Down here? Oh yeah, so to get acceleration from force, what do? Force equals mass times acceleration, so you divide this number by the mass to get the acceleration, right?
Alright, and what's the unit we're using for weight?
Weight is always a force. Yep. Okay. Any more questions on this homework? If the radius of the turn was this, oh, so this is what we did in the, this is actually the problem we did in the home, or in the example in the chapter 6 there. So look at the example in chapter 6, section 3, and you will be able to solve that one, no problem. Man, this is a great homework assignment. Only like 2 problems. Anybody have questions on it? Brooke, you're looking at me like, no. What's up?
How do you enter on like 13, 14, 15? It's numbers are like times 10 something. How do you enter those?
13, 14, 15. Ah, yeah. So times 10. When you're doing times 10 in this program, you do this. So if your answer is 4.2, put a lowercase e, or is it uppercase e? Yeah, I can't remember what it is here. I want to say it's uppercase e and do a -7 or something, whatever it is. And units, meters, or something like that. Let's see what happens. I don't know what the number is supposed to be here. What is it? I think it's a capital E, like that. I don't know, what should this number be? So if it's planet A is mass E, planet B has this mass, gravity pulls them together. So how far apart are the percentage of mass? So this is, so I have to take the inverse of, so I take the force, what's the force? 2.72 E. I don't even know how to do that here. Just calculate it. Oh, here we go, times 10 to the 27. Whoops. 2.72 times 5 times divided by, rather, 2.4 times 10 27. Whoa! What did I just do?
It's uppercase E.
Is it? Okay. Yeah. So that's correct. That's the way to do it. Ah!
So which way are these forces pointing
I'm sorry?
in the car? Weight is straight down.
Of course.
The normal force, whenever you times by cosine, on the end of the curve.
So which one is that? The norm? You're talking about the normal force or the
Well, the normal force in the car when it's not moving.
the normal force when the car is not
Well,
moving?
it's gotta be going away from the center of the car. Now it's gotta be going forward with the car.
Normal force always means what? Normal force means something particular. It means it is perpendicular to the surfaces where it is touching. So the normal force points upward this way. up to the right in this problem, this way.
So the force net is towards the bank.
The net force points this way.
How do you figure out the speed?
The example in the book, section 3.
Oh, that's the tangent theta equals velocity squared.
Yep, that's the one.
What was that, Scott? I don't want to click out of it, I'll have to read it.
I'll show you the equation. It's right here. Here's the equation. Tangent theta equals velocity squared over r times g.
So we need velocity.
Yep. That is right.
How is there gravity?
Because it's related to the normal force. So after we did that crazy experiment yesterday, I discovered that my favorite science equipment company just came up with a new device for that I'm going to buy. And it has more capabilities. I'm going to buy a couple of these for next year. Oh, that's not the right one. Although that one might be,
Hey, turn.
yeah, this one you have to attach a motor to it, I guess. That's not the one I was thinking of. Not the one I found yesterday. Here it is. This is it right here. It's much smaller. It's only $350. I'm going to buy a couple of these. That's good stuff right there. And you don't have to fiddle with anything and watch a needle move. You just measure the force directly because it has a pulley apparatus on it that you connect your force thing to. Your force. So it actually just measures the force directly.
What's the unit for speed?
The unit for speed?
Meters per second?
Yeah.
Centrifugal acceleration meters per second.
Accelerations are always meters per second squared, so it's definitely meters per second squared. Should we start chapter 7?
What's the direction?
Scalar.
Direction of the speed?
Yeah. I'm guessing it does have a direction.
If it's a speed, it's not a vector, right? If you talk about its instantaneous velocity, it does have a direction which is tangent to the curve that it's traveling on. But if it's just asking for the direction of the speed, speed has no directions. Does anybody want a poster to commemorate the eclipse in Nebraska? I got a whole bunch of posters I gotta throw away. Nobody wants a poster? I don't know. I got this one, this one. That one's kind of cool. Long? Wallpaper your dorm room. You can wallpaper your dorm room with all of them if you want. You have a wall that's like a commemoration of the. I got two of that one. The bottom one is the same one. So this one might be a little bit bigger. But they'll all be. This one. Here's another carrot. shows where it should show. This one. Actually, yeah, this one. You're just passing over Nebraska.
The wait times cosine theta are the three directions for
What's that?
you said wait times cosine theta is proportional.
Yeah, but that's not what you should have done. But I calculated your number before that.
That's the net.
Well, I calculated it first. So this one would be n times g times cosine theta. Right? This one.
Mass times gravity is weight. Cosine theta. But theta is
Well, let me go check the coding again. See if they entered it. Yeah, I thought they entered it.
that should be it for the normal force of the car set in steel, right?
Should be mass times 9.8 is the cosine. No. It's actually divided by the cosine of the angle. So they were doing it correctly. I thought it said times, but it actually says divide. So what I was doing was wrong. That's my bad. Okay, so I told you wrong on this one part here. I read the code wrong. I need to read more computer code, I guess. The computer code did not say times cosine theta, it actually says divide by cosine theta, which means that that is the moving one. So let's take a look at this picture again. Here we go. Okay, so if we're talking about the normal force when it's moving, that changes things. Essentially, the normal force becomes I need a new picture because this one's too messy. Clear all. Okay. See if I can do a better drawing with this mouse. Nice clean drawing. Maybe. It is extremely difficult to draw cleanly with a mouse. Okay, so here's our car. Here's our weight.
Weight and mass times gravity.
That's right. Now, if we're moving, if the car is moving, the normal force would usually be this force that is counteracted by the weight down here. But when the car is moving, the normal force is much bigger than it would be in that situation. So I'm going to draw it much bigger. And you feel this when you go around a bank turn. You actually feel like you're getting pressed into the seat, but really the seat is being pressed into you. And the reason for this is this component of the normal force right here. This component of the normal force is the thing that contributes extra to this normal force up here. And that's the only thing that contributes extra to it. In other words, the vertical component of this normal force is still being canceled out by some other thing, right? Let's see here. Is that the way I want to do this? No, I don't want to do that. I'm going to put this into, I'm going to change this into the parallel perpendicular components really quick and draw this out. So in this case, we've got, this is the centripetal force, which is also equal to the net force. And if this is equal to the net force, then everything else in here has to cancel out. This is the only thing that's going to be left after we cancel this out. Well, that means, and this is just a component of this force. Actually, I can leave it in normal components, I think. Let's just leave it in normal components. That means that the vertical component of our normal force here is actually equal to the weight of the car. So I'm gonna leave this in normal format. I like that better. So this one right here is equal to the weight. You could think of that as. But this one over here is equal to the centripetal force. So how do we calculate our normal force from those two things? Right? And we did this before we calculated the net force. Is that right?
Yep.
We did that. Okay. So we're calculating this before this. So this one being the weight here, then this one and let's see which one is our angle. Oh, it's not. It's a different angle. I'm missing something and I can't see what I'm missing. I think I figured that. Where's my... This is what I'm missing right here. Right here. Yeah, okay. I've got it right. I just not looking at it right. Okay. I've got everything right in here. We got to look at it a different way than I was, and I was having a hard time figuring that out. Okay, so here we go. So this, the normal here and the weight here Shoot, I'm still not seeing it right. They've got to go the other way, but it's normal and the weight. So the normal times the cosine of theta gives me the weight. Okay, that's right. Open that. So this is the correct. This is the correct triangle. This is theta actually, and this is theta. It doesn't look like it because I've drawn it badly, but this angle theta and this angle theta are the same. So we have to write an equation that's going to relate the normal force, this longer one, and this weight force. Well, this longer one is the hypotenuse to this triangle here, right? So if I use the hypotenuse times the cosine of theta, I should get this component, which is the weight, right? So I draw my equation, I write my equation, which says that the weight now equals the normal force, which is the hypotenuse times the cosine of theta. But in this equation, it's different than we've done it before, because before we've just plugged in the numbers and gotten out the weight. But we know the weight. The thing we don't know is the normal force this time. So we have to divide both sides by cosine of theta, right? And that's where that equation comes from. And that's what I was just seeing it wrong up here. But so this becomes our equation for the normal force this time. Normal force equals weight divided by cosine of theta. And the reason it becomes like divided by is because we didn't rotate our axes like we have before. Before, we didn't do it this way because we didn't want to mess with dividing by things. We wanted to mess with rotating the axis because it made it easier. But now it makes it easier to not rotate the axis, to write the weight as a component of the normal force, right? And then calculate the normal force from the weight divided by the cosine of theta. So that's the difference there. Sorry for that confusion, but that still is that's in this example right here. That's exactly what they calculate right here in the example that we did previously. That's this equation right here. So, okay. Any more questions on homework for chapter 6? I honestly think chapter 6 should be combined with a different chapter, with another chapter, with the rotational dynamics chapter. Whatever.
Is the acceleration, the centrifugal acceleration, is it no direction? Because the way it goes?
Centripetal acceleration. Centripetal acceleration always points towards the center of the rotation, center of the movement. So if you're moving in a circle, it always points towards the center of the circle. Because it's always turning you towards the center. That's what centripetal acceleration does. It just turns you towards the center of your motion so that you keep going around in a circle.
I was having some trouble comprehending the centrifugal acceleration, and I started thinking of it more like how the normal force, the force pushing something back up from its weight. Is it kind of
Nope.
similar to how centrifugal acceleration
Not really.
mindset?
Here, I'll teach you centripetal acceleration. So we put the United States on this to make it look like the Earth. So we can do the eclipse on they made an eclipse across the United States by putting a moon out here and making a shadow across the moon. Let's get a different one. Okay, guys. Philip is going to demonstrate for us centripetal acceleration. Okay? You gotta stand up. You're let's see. You're going to be you're going to keep this thing going in a circle using only this. Okay? I'm going to give it some velocity along the edge of the circle, and you have to keep it on the edge of the circle. Ready? No, you're not going to stop it, you're going to just push it. Only push it. Ready? Okay, so let's try it again. I would suggest you start pushing over here and not start in one place. I would suggest you move while you're pushing it. Okay? Keep it on the edge of the circle. Okay, you stop it. I don't want you to stop it. How are you gonna
Okay, let's find
Are you ready? Ah! So which way are you pushing it?
straight in.
You're pushing it inward, right? So let me show you another way to do it. And you're not slowing it down, right? It didn't actually slow it down. Let me show you another way to demonstrate how this is done. Now I only want you to hold it at the top like this and do the same thing. You can hold it with your hands. But you're going to do the same thing. Hold it harder. I need to buy one of those things called that the people do when they're marching and they twirl around and throw it on a baton. Those work really well because then you can hit the ball.
Tennis racket.
Tennis. I got some tennis rackets. I break the tennis racket. Okay, ready? I'm going to try this one. So you're always pushing it towards the center, right?
Yes.
But you're not actually slowing it down. The only thing you're doing is turning it. Right? You haven't even applied any force that would slow it down. It's only turning it. That's what centrifugal force does. That's why centrifugal acceleration is towards the center. It only turns it. It doesn't slow it down or speed it up. Tell you the truth, that was the only reason I had to paint this circle.
Was to do that experiment?
Yes. I found a lot of other uses for this circle, but that was the main reason for it.
That actually makes a lot of sense, though.
It's a very difficult concept to comprehend without doing that in scenes.
You've got to push it inward in order for it to stay on.
That's right. It always has to be pushed inward. This is what's happening with the Earth. If the Earth's gravity turned off, the moon would just go off in a straight line. But it's always getting pulled back. So the moon tries to go this way, and it gets pulled back this way. And it tries to go this way, tries to get out of orbit. So what they say is that the moon is actually falling around the Earth. It just moves forward enough so that it never falls towards the Earth. It always falls around the edge of the Earth. And that's what orbit is. It's falling around the edge of the Earth.
Rubbing yourself around this.
You're turning just enough to fall back to the place that you were at before. And you're doing it continuously and constantly so that you have a circular path.
And let's talk about gravitational force.
What is?
Following statements through regard, I got gravitational force increases as distance increases, gravitational force causes ocean tides, gravitational force equals.
So this one I would really bring up the equation for gravitational force and see if each one of these things applies. So what is the gravitational force equation? Right there. We have it. Starts with force equals. There's a bunch of letters. So, mass times acceleration is the general force equation. But for the gravitational force, it starts with a big G. Now, what kind of things attract each other gravitationally? What do you have to have? Not necessarily big objects, it can be any objects, but they have to have something with gravity. They have to have not magnetic, they have to have mass. So you have to have mass 1, mass, that can be times mass 2, and then there's another thing that matters. What matters is according to Newton. Mass 1 times mass 2 divided by divided by r squared. This is Newton's gravitational force equation. So, if the mass is bigger, does this number get bigger? So is A correct or not? And so on. Just answer every question like that. You look at the equation and see if it changes and how it changes. Any other questions? Number 7? What's number 7? Yeah, you need to have your equation. You have your equation? What's the equation? It has a great big G. There it is. There's your equation. So you look at this equation and you say the first one says, if the mass is bigger, the force is bigger. Is that true? Well, look at that equation. What happens if the mass is bigger? Is the force get bigger? Absolutely. So for bigger forces, for bigger masses, the force gets bigger. So then you ask the next question. What's the next question? Wait, what's this one? Oh, sorry. This is the wrong one. Oh yeah, this is supposed to be multiplied. And then it's not over R, right? Instead of being over R, it's over. Good.
On this one, I don't
What would be the mass of the second object in terms of variable? Okay, so you take that equation and solve it for mass 2. One of the masses is going to be mass 1, the other is mass 2, right? Solve this equation for mass 2.
So, here.
Yeah, divide by mass 1.
So the gravitational force decreases as the distance increases between two objects. That's true. Gravitational force falls as the gravitational force. Not a contact force, but
Gravitational force is what causes our weight. Right? If our weight, if we're standing on something, gravitational force causes our weight. It's also
why didn't you tell me that before we came here?
I did say
Pick
that.
it up.
I thought it was self-explanatory.
Gravitational force is
she
not,
said everybody.
not gravitational force is not weight, it's what causes it.
It's also
It's weight, it's a measure of weight.
Yeah, it's also known as the gravity of the situation. Should always listen to Brooke. That's what they teach in school. And Nebraska. And California.
So this one here is
What is this? Okay, so this is R squared. So put R squared. And this R up here is not what you think it is. It's actually a vector. It just tells you which direction it goes. It tells you which one it goes. So when it has a little line under it, that means it's a unit vector. We don't talk about unit vectors in class. So I usually don't use this thing except for the mechanics stuff. Not something along the way we There's some other times we'll use it, like we'll use it here, and some other places we use it in, and stuff. I try to stay away from Some of the other equations get confusing. And that figure out is the same as the line. Those things are often interchanged in physics. It's just a fact of life. I will be right back in a few minutes.
Two objects in common gravity and the distance increasing.
Happy to I want to go blow some bubbles. Yeah. Should see some of the bubbles we made last Saturday. They're huge.
How did you know? Tell me that my hands didn't feel. Instead of that, what word did you use?
Exfoliate?
Thank you.
Yeah. People pay a lot of money to get exfoliation, man. You must owe the STEM Club some money. Spa treatments. Yeah.
How can you figure this out if you don't have any other information? Two objects attract each other with gravitational force of 58 degrees. Distance separating them increases by 2 times. You can't just take 58 divided by 2.
Oh yeah. Just call the distance r. So write down the equation, f equals, what's f equals? It says right there, 50 meters, right? Equals, and it's going to be g times m1 times m2 divided by r squared. Okay, good. Now write a new equation. Now we're going to say F equals C, because we don't know what the force is going to be now. So let's find out what it's going to be. F equals G. And M1 and M2, those things haven't changed, right? What's the only thing that's changed? Yeah, so instead of R, it's going to be up. So go ahead and put your divider in. And you're not going to divide by R, now it's now the R is increased by double. So what is double R? 2R. Now, no, it can't be 2R squared, it has to put 2R parentheses squared, right? Because you have to square the two and the right? Now, this equals, what equals something? G times M1 times, it doesn't equal 58, this one equals, we don't know. But it's going to equal G times M1 times M2, because that doesn't change. But the bottom becomes 4R squared, doesn't it? So what's the difference between this answer and this answer? This one's multiplied by 1/4, isn't it? Compared to this one. Right?
You talked about
There is a 1/4 already. Here's a 4. This one doesn't have it, right? You don't have to. In other words, this force is equal to this force divided by 4. So you say that F equals 58 divided by 4. Because this part, the G M1 and 2 over R squared, that's equal to 58. It's right there, that's equal to 58. So this part is equal to 58, but if you divide by 4, it's equal to the new force. So you take 58 divided by 4 and you're done. So all I've shown you is I've shown you the calculation twice. I've shown you the calculation once where we know the force. Then I've shown you the calculation again where we know how the difference changes from the original distance, but we don't know the force. And then we compare the two answers. This answer says that G times M1 times M2 over R squared equals 58. This one says our force equals G M1 M2 over 4R squared, which is the same as this except for that 4. So if I erase that 4, the rest of this is equal to 58, right? So if I divide 58 by 4, I'll get this. Let me write one more thing for you. This,
I understand it, I just don't understand
this,
how we know that.
well, it all has to do with, let me give you an example that has nothing to do with it, okay? So I've got two cars. So this car is the standard model, right? And it costs $1,000. New car. Same exact model and everything, make, year, everything else, except this one has a spoiler on it, and stereo, a different stereo upgrade, speakers, and it has blue headlights, which are popular nowadays, and this one costs $1,500. How much does a spoiler or stereo and blue headlights cost? $500. What? How do you know that? Just explain how you did that. How did you come to that? You said, well, this one was the one that I had. This is the one that I have now. The difference is $500. Here's the one that I have. Here's the one that I have now. What's the difference? 1/4. So I take the one that I had and divide, I multiply by 1/4, or divide by 4, you get the one that I want, right? In this case, I added 500. In this case, I divided by 4. Same kind of thing. Exactly. So there's your standard model. This is the upgrade. That make sense now?
Yeah, it makes sense for the fact that I don't know. Like,
These kinds of things are the things we're trying to. this is really what we're trying to teach in this class, is to look at a situation and say, what are the different ways that I can approach this to make a solution? And there's obviously just so many different ways you can approach something to get a solution. So we're trying to give you as many of those different experiences as we can that are not necessarily just physics solutions. You know, this kind of solution can be applied to many things in your life. And that's what we're trying to provide for. Okay, who wants to go out and blow bubbles with me? Sure. Too cold? It's like 60 degrees out there.
Cold in here.
It's good. I'm gonna go blow bubbles.
You guys are back with the normal force. It's your final results stuff about the
just wanna take that stupid air conditioner and throw it out and just break it.
Super cool.
Hat, never,
Plus.
jacket.
What about 7? What do you think, just reform the, Radio team wins big. Did he eat on after me?
Tell you the last one. Second one. Was your acronym third one.
Boys rule and girls drool. I can't help it, I'm sorry, buddy. I shouldn't say that.
Six.
Did anybody do any work on the clock?
No.
I'll have it right here.
Yeah. Wednesday is the one day I cannot.
Wednesday is the only day I get off, and I'm not coming in here on my only day off.
Yeah, Wednesdays I'm in class from 9 to 11, 1 to 2, 6 to 9.
But I did buy me new pencils yesterday, even these cost $10 for 2 weeks.
Jesus Christ. Very good.
Yes.
Where?
See, they used to have them too, my kids too.
See what I wrote, right?
Oh, thanks.
I had a cell phone that disappeared for 8 months. None of my kids knew where it went. I thought I lost it. Then around Christmas time, we were cleaning up kids' rooms because they got a bunch of stories and shit. And I finally had a cell phone in my daughter's bed. She'd stolen it so she could play damn video games and I forgot where she put it. Yeah. What sucks is I had a SIM card in there and since I couldn't find the phone, I couldn't afford a new phone. I had to drop the phone number that I had for 10 years.
That's what.
Yeah. And I think long as it's in use, I don't care what girlfriend was. Because a friend of mine called that number and some girl answered.
You know who it was.
If you're another dude, then really be going like, your man, he's my man. Yes.
Oh, God. There was this horrific, it was a
Wow.
YouTube burn where basically it was a bunch of gamers and this guy paid another guy to find out his girlfriend was screwing out on it. And he paid this YouTube live streamer to set up a burn on her where they were gaming, she was gaming, and they had her recording, she live streams too. They set it up so they thought that she couldn't hear them and they were talking about each other. And she starts losing some shit. And it's like, it's really funny. She didn't even know it. We know the shit she did also. Yeah, I had cameras set up in the bedroom in the car. But she doesn't even know it's there. It's hidden behind the thing. And they usually hear that. She ran and checked the video. And on the video, he had a message saying, "Surprise, bitch. We just set you up. Enjoy being famous." And she's melting down. Either if it was a complete stage thing where she was in on it, then she would be an actress. She had that genuine, you know, the quiet stare.
Her little party. Her
think it's ground. You got centripetal force is the same as in that force. Centripetal is the same as in that force. It's the question. Centripetal force always points where? I'll have to put it back. Why did you have me push the bowling ball? Centripetal force always points where? Straight towards the center. Where's the center in this scenario? Yeah, no, it's right now. You tell her.
Working on it. Fight you.
Are you gonna be in there for a while? How long can you operate on that?
I'm gonna slow you
Did anybody work on that,
All that. You know, still in here?
Bob,
We need it.
Oh,
Wait a second.
he was my help.
Yeah, we can help you,
yeah,
but I have FG to.
Oh, yeah, I got
What do you have?
Not that.
What do you do when one?
I reworked the formula wrong. That explains it. Explains a lot. Cool. My brain started. This formula tell you?
that's it.
It's temptation. Little tinkering project.
Oh, yeah, right.
Yeah, that's an awesome project. And they had one thing on there, they had different blocks that I would have thought, I wasn't sure if they were functional or just blocks. And they were the division blocks, they had two different ones. So I think verify whether or not they are actual functional blocks that are on the wall. I had part, but I had it because it's see, that's the purpose. That's the best. Y'all are doing well. No, it's over here. Ignore the 20 G. So, velocity is very correct? So, 6.63 squared. That is how much you, 37.17 per second squared, divided by. Yeah, I was no, it's just G.
See you later.
started off.
Oh, that's good. So you're grabbing.
Yes.
Yeah. Wasn't mine.
All right, I guess we gotta do physics again.
Stop that video.
Huh?
I don't think you ever stop that.
Oh, you're probably right.
It's
Okay.
just been hearing us like, get mad.
Dang it, I hate this teacher.
No, we love you. Just hate this.
Oh,
Stupid and you
aggravating.